So this is feedback for the IB Paper 2 specimen that was done in 2025 February. I'll make a few general points as I'm going through the paper, but one thing I'd like to highlight at the start, hopefully when most people are listening, is there's a big box here, right? You've got to try and fit your answers within that. If you don't put it in the box, leave a note to the examiner. I'll mention this in class as well, but do try and squeeze things within the box if you possibly can. Make sure your units match. Write down the units for everything. Show you're working out all the general stuff which you should know. So question one, like always, is a calculation question. I recommend doing lots of question ones if you struggle with this one, because it's always going to be calculation at the start of the paper. It seems to be what they do. So you've got to work out, what have you got to do? You've got to work out the empirical formula of a compound HX, which is clearly made of carbon, hydrogen and oxygen. Right, so the number of moles of carbon, or I should say the relative number of moles of carbon, because it's percentage given, percentage of a mass given. So you can treat it like mass. So the number of moles, or relative number of moles of carbon given, is 39.99 divided by the value for carbon in the data book, which is 12.01. That comes to 3.33. Do the same thing for hydrogen. Number of moles of hydrogen is equal to 6.73 divided by, it's 1.01 in the data book. Number of moles of oxygen is 53.28 divided by 16.00 in the data book, comes to 3.33 again. You look at those as a ratio, so 1 to 1 to 2. Oh, I didn't give an answer for that. That's 6.66. There's a 1 to 1 to 2 or 1 to 2 to 1 ratio, so you have to write it as an empirical formula. So carbon is 1, hydrogen 2, oxygen 0. The next question you're asked, you've got 25 centimeters cubed of a solution of HX, and you've got 1.51 grams of it. You're titrating it with sodium hydroxide. So we know it's HX reacting with sodium hydroxide to give NaX and H2O, so it means they're reacting in a 1-to-1 ratio. You're told, you've got some information here, you're told you've got concentration of the sodium hydroxide is 0.750. You're told the volume of that is 22.30 centimeters cubed. And so the number of moles of that can be worked out. You're also told you've got 1.51 grams of HX, but we'll come back to that in a second. So if we work at the number of moles of sodium hydroxide, we do that times that, comes to, or divided by 1,000, comes to 0.01672. And you've got a mark for showing the number of moles of that. And that's obviously equal, given it's a 1-to-1 ratio, 0.01675 moles of that. Now you're told, aren't you, the mass of, you're told the mass of the HX in grams. Moles equals mass over mR, so mR equals mass over moles, and 1.51 divided by 0.06725 comes to 90.28, 90.3 grams per mole. Okay, that's that. So you've got a mark for that and a mark for getting the right answer there. So then you have to work out the formula of HX. Sometimes you have to show working here. This time you just have to state the answer. So you know the empirical formula is CH2O, and if you add those together, that comes to a mass of 30, and there must be 3 lots of those in the formula HX. So it must be C3, H6, and O3. So it's just 3 lots of that, and most people got that right. And then you were told that HX reacts with sodium hydroxide, according to that equation, 1-to-1 ratio, which we worked out anyway. Identify a functional group in HX. Now the only thing this could possibly be is an acid. So the only acids we know about, the only organic acids we know about, given it's carbon, hydrogen, oxygen, are carboxylic acids. And the functional group in a carboxylic acid is called a carboxyl. And you got the mark for saying like that as well, so carboxyl group. Okay. You're given the IR spectrum. I know you're pretty new to IR spectra, and I did say there'd be no spectroscopy. I lied a little bit, but you'll get over it. Identify the functional groups shown by the bands at Y and Z. And this really, so you see two things about this position. You see kind of sharp peaks, which are due to CHs, which they're in every spectrum. You can't see them here because they're covered by a big fat broad peak. And that broad peak is due to that, so that's going to be that one, an OH, an OH bond. You can't tell what that's necessarily part of. You just told that it's all you can do is work out that it's an OH. And the other thing you can work out is you've got a C double bond O for the Z. That's a classic IR peak that you're going to see again and again. So you're then asked to work out, or give you a suggestion of what the compound could be. And you've got 3 carbons, 6 hydrogens, and 3 oxygens. We know we've got 3 carbons, so how about that? And we know we've got a carboxylic acid, so there's not much else we can do. We've only got 6 hydrogens left and 1 oxygen left. Well, how about we just stick an OH on there? There are really very few things you can do with those number of carbons and hydrogens. So that gets the mark. The alternative with the hydroxyl on the other carbon is also allowed. They'd both be reasonable structural formula that are consistent with all the evidence. Just notice when I was just scanning back through there's an expression monoprotic, that if you don't know what that means, it means it can release 1 hydrogen. So sulfuric acid, H2SO4, is diprotic. Monoprotic is things that can release one hydrogen in its acid. So carboxylic acid would be a good example of that. Drop that in there. The next question was really, I think the students that studied physics or particularly enjoyed physics are going to have enjoyed this question more. And I'm not going to read through the questions. This is something you've done at GCSE and IB, but alpha particles slapped beamed towards a thin sheet of gold. Some will go through, deflected a bit. Some will be rebounded, repelled back again. There's a graph there showing the relationship of those. Why does some follow path 2, that rebounding? And really the word I'm looking for there is repulsion. So it's repulsion between 2 positive charged things. So the alpha particle is positive charged, and the nucleus is positive charge. So I haven't written it out very well, but the repulsion between the 2 positive charged species, the alpha particles and the nucleus. So most of the particles pass straight through. Suggested conclusions have done well, actually. The conclusion is that either you could say that most of the atom is empty space, or you could say that the nuclei are really tiny. Both of those get the mark. Most people did. But then we struggled a bit with after this. So, right, where it says outline the appearance, what it means there is give a brief description of what the helium spectrum looks like. And you are expected to know that, believe it or not. And I'm going to tell you exactly what it says in the mark scheme, if I can just find it. Is it somewhere? The mark scheme says a series of lines, or a discrete series of lines, which means separate lines with different frequency or different wavelength. So this is an emission spectrum, so you'd see lines given off by the machine. So if you describe the line, that's a terrible looking line spectrum, but you simply have to describe it. So outline the appearance, a discrete series of lines with different frequencies of different wavelengths. Have a little look at it, make sure you understand what's going on in an emission spectrum and an absorption spectrum. Make sure you know those in detail, can describe them as essentially instances graphs, right? So emission spectra of 1 electron systems It's important, that becomes important in a second. Can be explained using a model of the electron attracted to a nucleus by the electrostatic force, right? Some energy levels for the helium ion are shown. So there's a 2 plus nucleus and 1 electron. Okay, so this works for 1 electrons. Explain how the frequencies observed in the emission spectrum support the idea of an electron occupying discrete energy levels. So the word discrete there means separate energy levels with gaps between them. It's not like a sliding scale where it can be here, 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 anywhere up there. It's either going to be here or here or here. That's what discrete means. And I thought this was quite hard to get the mark, and so this might be a reflection of the fact it's a specimen mark scheme. There's some other issues with the mark scheme I'll talk about. But you have to be clear that the energy of the photon that's given off is related to the frequency of that photon. So energy of photon is related to frequency of the photon. Okay, and that might have come out as part of a descriptive answer that some students gave, the full descriptive answer of what's going on, but making it clear you understand that the energy of the photon is related to frequency, because we're relating energy to these frequencies of light we've seen up in the spectrum, right? For the second mark, you've got to be clear that the energy is also of the photon is also dependent on I think this is where people struggled, the difference in energy levels. So the delta E, in other words, the energy difference between, say, there or there and there or there and there or whatever. Okay, so it's the difference between the energy levels, where it says in the mark scheme. So that's what I'll write down. Difference in energy levels. If you do old past papers, it'll have some questions like this, and you expected to know for the old syllabus that emission down to n equals 2 are the ones that release light, visible light that we can see. Anyway. Deduce the ionization energy of the helium ion. So in other words, going from helium plus to helium 2 plus an electron. You know the definition of ionization energy is the energy required, I emphasize, to remove 1 mole of electrons and 1 mole of gaseous substance, in this case 1 plus ions. And so energy required to go from this lowest energy level out to essentially n equals infinity. So it's that gap that requires 1,000. So 1,000. It requires 5,250 kilojoules. 5250. So people that were putting minus 5250 were going to get the answer wrong, because it's an endothermic process. Ionization energy is always endothermic. And of course, it's the energy required to remove the electron from the lowest all the way out to an n equals infinity. That's what ionization energy is. This question was answered pretty well, periodicity question. Why is ionization energy of hydrogen atom smaller than ionization energy of helium ion? So if you weren't actually thinking about what those things were, you were going to struggle. So let's just draw those quickly. I'll draw them at the bottom for space. So helium ion is 2 protons and 2 neutrons with 1 electron. That's the energy required to remove the electron from there. Whereas a hydrogen atom is simply 1 proton, 1 electron is the energy removed to remove 1 mole of electrons from 1 mole of hydrogen atoms. So similar in lots of ways. Slightly stupidly, I drew them the wrong sizes. But the first point to make is the helium nucleus is more attracted to this electron because it's got a 2 plus charge. So it's a 2 plus versus 1 plus charge. You say the helium nucleus has more protons, is more positively charged than the hydrogen nucleus. And the other thing, of course, because it's got 2 protons, it's actually a smaller ion as well. So I shouldn't have drawn it like that. I should have drawn it like hydrogen atom like that. It's actually slightly bigger. The second proton brings that first shell in a little bit, making it a tiny bit smaller. And the closer the electron is to the nucleus, the harder it is to remove. So as per the Mark scheme, all you've got to say is that the hydrogen atom is larger. Simply that will do for the Mark. Why does this work for He plus and not He? Well, the thing about He is it's got a second electron in it. That's hydrogen. That's a helium atom, and it says on the previous page somewhere that this works for one electron systems. As soon as you get a second electron, it all goes a bit wrong, all gets a bit complicated, to say the least. And it is due to electron interactions. And essentially, those things they're actually interacting with one another. They're repelling one another. Electron interactions must be considered. And that makes the whole thing far more complicated. Okay, why this is a silly question? I thought I didn't really know what it is I'm trying to get at there. It's super vague. I gave most people a mark here. Why has the model of the atom evolved over time? So something about new evidence, new technology developing, developments in the models, all sorts of things you could have got answers for there. Right, question 3 wasn't as hard as people thought. Okay. There was one or two bits of it that were quite tricky, but it wasn't as hard as people thought. But I understand that this would be maybe the first time we've seen anything quite as complex as this. Lithium-ion batteries are an important modern development, obviously, good to be aware of. But you've got, in the anode here, you've got just lithium. Lithium's held in a lattice. So something's happening to the lithium down here. There's an electron. The electrons are flowing from the anode to the cathode via an external circuit, and that's where the car might be, if you like, that's being pushed along. So something's got to travel through there. So if electrons are going that way, I mean, I think it should be obvious that it's a lithium ion going that way. But let's start off with the top equation. What's happening at the top there? If we simply realise this is just a balanced equation, but given it's happening at a cathode, there must be an electron involved as well. So let's have a look. So we've got one lithium here, two lithiums there, two cobalts there, two cobalts there, because this is times by 2. We've got 4 oxygens on this side, and we've got 4 on this side, 2 times 2. So anything that's missing is a lithium. And obviously we're adding an electron, that's the whole thing, so it must be a lithium ion and an electron. So the lithium ion comes from the anode. Lithium ion travels through this region here, and the electron is travelling around the outside. Okay, so the species moving is the lithium ion, and at the anode, therefore, it must be simply that the lithium is giving up that lithium electron to form a lithium ion. There we go. So it might be easy to start from the bottom or the top, but that looks like a difficult question because you've not seen necessarily that detailed diagram of a lithium ion battery before, but it can be sort of unpicked. This question should be relatively straightforward because it's a spontaneous chemical reaction. First of all, the delta G for that reaction, this discharge, must be negative, and E cell, if it's a spontaneous reaction, must be positive. And you're also told that it's an increase in temperature, so it must be exothermic, so that must be negative. It's only worth 1 mark, but that was mostly done pretty well. Now this question, the mark scheme, simply says something that I don't really agree with, and I'll explain why. So the mark scheme says delta G recharge is greater than delta G discharge. Now, to my mind, the equation for the recharge must be exactly the same but opposite to the discharge, which means the delta G must be exactly the same but opposite. So it could be that you could argue that if, say, the delta G of the recharge is minus 100 kilojoules per mole, you'd expect, so that's the discharge, and the recharge would therefore be 100 kilojoules per mole. And that means you could argue that that number is a greater number than that number, and that's maybe why people put that as the answer, including the mark scheme. But it does say compare the absolute value, and I've checked with mathematicians that absolute value means the number not including the sign, the modulus if you like. So they're both 100. So if you said they were the same, I gave you the mark. If you said they were equal and opposite, I gave you the mark. Or if you gave the mark scheme answer, I gave you the mark there. Righty ho. This is an interesting little question. So it's a funny one. I think I've marked it wrong. I'll explain why, and I'll talk about it in class as well. So you're told here that you've got equal masses, and the masses is important, of potassium and lithium. And so let's say we use 0, 1, 2, 3, 4, 5, you don't have to write the numbers on here, grams of potassium and lithium in that reaction. You'd have to find out how long in each of these cases it would take to react completely in a simulation. Right, so you'd expect potassium to react much faster. Also, by the way, you get the first mark for drawing a graph with a positive gradient in each case. I'm just going to draw that for one of them. Whether you've drawn it as a straight line or a curve, it doesn't matter. As long as it should start at 0, shouldn't it? But it should increase. The bigger the piece of potassium, the longer it will take to break down. So you get a mark for what's it worth? It's worth 2 marks. You get a mark for drawing a line or a curve pointing upwards for both of them. But which one should be steeper? Now, I would have argued that the potassium one should be steeper, and many of you did that, and I gave you the mark, because it reacts faster. Potassium reacts faster than lithium. It's much faster reacting than lithium. But in the mark scheme, it says that the curve for lithium should be higher. It should be like that. And if I've marked it incorrectly, do come back to me and get that fixed. And the reason that this should be steeper, I think, is that the number of moles is going to be significantly different. So the formula mass, the atomic mass of lithium is 7, the atomic mass of potassium is 39, I think, thereabouts. And so if you've got 5 grams of this stuff, you've got under 1 mole, just about 5 grams, or moles equals mass over mR, so just under 1 mole of this stuff. You've got way under 1 mole of this, so 5 divided by 39 is a much smaller number than 5 divided by 7. So you end up with actually this one being faster because it's less lithium, so it's going to end up reacting faster. I don't know how predictable that was. I don't really like the question, if I'm honest. And that relates to part 2 here, which is that there's no point in comparing 2 different masses. It's not a valid measure of reactivity because you've got different numbers of moles. In each case, there's no point comparing apples with pears. It's very difficult to therefore predict what the outcome would be. So I didn't really much like that question. Lithium carbide really threw lots of you off though. This is a bit of a battle for most of you. So question either the lithium carbide, one of many lithium and carbon compounds. What's the percentage covalent character in this type of compound? Use sections 9 and 17 of the data book. Right, the bit in section 9 is the electronegativity. So the electronegativity of lithium is equal to 1.0. Electronegativity of carbon is equal to 2.6. So that's the first bit you need to make a note of. And in order to understand this, you need to look at the other section of the data book, which is the Van Arkel-Ketelaar bonding triangle. So the first thing you've got to do is work out the difference in electronegativity. The difference in electronegativity between those two is 1.6, and the average electronegativity of those two numbers, is 3.6 divided by 2 is 1.8. You get a mark for working all that lot out. If you then simply plot those numbers on the Van Arkel-Ketelaar bonding triangle, you can see roughly it kind of comes pretty near the middle of it, and it's 50% ionic and 50% covalent character. You get a mark for being clear that it actually falls within the ionic section of the triangle, which is slightly confusing given it's roughly 50-50. So it's in the ionic section, but it's got 50% or roughly 50% covalent character. Well, I don't know if you got that right. I think it's a slightly weird question, like a lot of these. In the specimen paper, the next question was much more routine. It's just a delta G. It's delta H minus T delta S question. You're given the information you needed in this question. So delta H was minus 62. T 298.15, and delta S, careful looks, it's given in joules per mole per Kelvin, so you did have to convert that to kilojoules per mole per Kelvin, which would be minus 11 over 1,000. If you chuck that into a calculator, it might be good if you just work it out bit by bit if you're not that confident using a calculator, but that came to minus 59 if you rounded to 2 6-figure kilojoules per mole. Please write the units, please make the signs nice and clear, and then ask you to draw the formula of the anion. Those of you who don't know that an anion, what the difference between an anion and a cation is, cations are positive charges and anions have negative charges. So the anion here is clearly not anything to do with the lithiums at all. You all know that lithiums are plus ions, so we can ignore those. It must be a C2 2 minus ion. So what on earth's going on there? Now this first point I make is essential for getting your head around drawing these sorts of things. You've got to, your Lewis structure that you end up drawing has got to have the same number of electrons in it, same number of valence electrons, as 2 carbons plus 2 negative charges. So each carbon's got 4 in its outer shell, so there's 2 lots of 4 electrons, and there's 2 more because it's negatively charged, plus 2, that equals 10 electrons. So your Lewis structure has got to have 10 electrons. Right, I'm going to draw all 3 possibilities that I can think of, and only one of them can be right. So I'm going to draw, I'm not going to tell you which one's the wrong one just yet. The 2 carbons are joined with a covalent bond, and in order that they have full outer shells, I've drawn 8 electrons around them. There's that one, or there's that one. Okay, and the only one of those, well, this has got 2, 4, 6, 8, 10, 12, 14 electrons, so it can't be that. This one's got 12 electrons, 2, 4, 6, 8, 10, 12, so it can't be that. This one's got 10 electrons, 2, 4, 6, 8, 10, so it must be that. But please don't forget to put the square brackets and the charge around it. And please make sure your dots are really clearly visible to any examiner who's reading it on a scanned page. Once you've drawn that, you can work out the hybridization is SP, and lots of you did. It's SP because each carbon has kind of got 2 domains coming off it, triple bond and the non-bonding pair or lone pair. So it must be SP there. The other 2 p orbitals are making the 2 pi bonds in that system. Getting there. Right. First thing to do with a question like this is look at the blinking mark, see how many marks it's worth. You've got to realise there's going to be a number of things you've got to get right to get 3 marks for this one. So you're told a value, you're going to have to use that value. If you're given a value in a question, you're going to be using it, right? And you're told it's hydrochloric acid, which you know is a strong acid, strong monoprotic acid. So you can work out the pH of that strong dilute monoprotic acid by doing pH is equal to minus the log of the H plus, which in this case is equal to minus the log of the HCl concentration because it's a strong acid. Weak acids you do a different calculation obviously, but it's all you got to do is minus the log of 0.1, and that comes to 1. So you get a mark for starting your graph there. I'd even mark that with a cross to be really showing the examiner know what I'm talking about. That gets a mark. And then you're adding distilled water to it. You make it more dilute, the pH is going to go up, isn't it? Again, you knew that at GCSE. You do tenfold dilution, it will be pH 2, tenfold dilution again, it will be pH 3, tenfold dilution again, it will be pH 4, and so on. But this is never going to get to pH 7. Right? It's an acid. It doesn't stop being an acid just because you add more water to it. Now, this idea of it going up in 1 unit per time works, it's true. But of course, when you get to pH 7, you've got to start taking into account the fact that this acid is extremely dilute, and the concentration of hydrogen ions that are present in neutral water are playing a role as well. So you're always going to have more than the hydrogen ions in water. You're always going to have more than 1 times 10 to the minus 7 moles per litre of H+. So it's got to finish, the graph has to finish somewhere below 7, anywhere below 7 would do, and then some sort of line going up. It's actually a curve, but any kind of line going up to somewhere below 7 would be absolutely fine for 3 marks. 1 for finishing below 7, 1 for a line going up. Job done. The experiment is repeated using 0.1 mol per litre ethanoic acid. The key thing here is this is a weak acid. And some of you have forgotten how to do the calculation for weak acids, so it's a good chance to remind you of that, a good chance to practice that. You've got to calculate the initial pH of the ethanoic acid. And this is worth 2 marks. Okay, so I'm not going to do the derivation of this. You're expected to know, ideally work out, but expected to know that the hydrogen ion concentration for weak acids is given by the concentration of HA times by the Ka. And so you can work out the Ka by doing the inverse log of minus 4.76. And the HA was given to you, so it's the square root of 0.1, which is the concentration of HA, times by 1.7378 times 10 to the minus 5. So if you do the square root of 1.7378 times 10 to the minus 6, which is those two times together, you end up with the hydrogen ion concentration, which I got to be 0.01318. Minus the log of that to get the pH, and that comes to 2.88. Okay, a very straightforward question if you've remembered how to do it. Okie dokie, question 4b. Transition metal chemistry. So, oxidation states here. The reason I paused it, I was just nervous I've marked this the wrong way around, but remember oxidation state, you always have the plus or minus first, then the number. Okay, so it's plus, then a number, and charge, it's always the number, say 2 or whatever it is, and then the sign, so X minus. Just remember that. I hope I've marked it the right way around, I'll double check them. Deduce the oxidation state for cobalt in this thing here. So, right, the complex is the thing in the square brackets, right? And that has got 2 chloride ions attached to it. So this complex, this thing, must be 2 plus because we've got 2 chloride ions. So the complex ion has got a 2 minus charge. Right? 2 plus charge because the chlorides are each 1 minus. So we've got a 2 plus charge. The complex, though, is 2 plus. Well, we've then got to work out the oxidation state of the cobalt within it. Now, ammonia, of course, is a neutral substance, so we can ignore that. It's got 0 charge. But chloride has got a 1 minus charge. So the cobalt must be plus 3 oxidation number there. If you treat all of the ammonia as a 0, if I just do it here to show you, this whole thing, doesn't matter how many of those there are for the purposes of this whole thing comes to 2 plus, That's 1 minus, they're all 0, so that must be 3 plus. Okay, so oxidation state of cobalt 3 plus. Describe the bonding of the chloride ions. There are 2 marks here, so these chlorides are different to these chlorides. This is a different substance. This is now with 2 chlorides within the complex, but those 2 within the complex are attached via coordinate bonds. The IB seems to prefer the term coordinate bonds, and I think that's fine, particularly for within a complex like this. And the other chlorides, you need to state which ones are which. The other 2 chlorides, that's just an ionic relationship, isn't it? So you've got a plus, or here we've got a 1 plus ion, and we've got a 1 minus ion, so it's an ionic bond. So there's the two internal ones. 2 chlorides are coordinate, and the other one is ionic, okay, between the chloride and the 1 plus complex. This explanation of colour of complexes is definitely worth something. It's worth practicing. It's often worth 3 or 4 marks, and I was a tiny bit generous for the first mark because it, I did allow any mention of D sub-level splitting, but the language in here has to be really precise. So what happens is if you've got a naked, say cobalt 2 plus or 3 plus ion, whatever, it would have a 3D subshell with a number of electrons there, however many it is. I've not got the number of electrons in front of me, so I don't know how many it is for cobalt. Doesn't matter. When ligands surround that complex, that 3D subshell is split into 2. So that's the first mark. So 3D subshell is split, and that's due to some sort of interaction with the ligands and those orbitals. Remember, all of these orbitals have different shapes, and so as the ligands approach, each of the orbitals is affected differently. Some of them go lower in energy, some of them go higher in energy. Overall, they have the same energy as these 5, but you get that splitting. So 1 mark for that. The second mark is to show that you understand that you've got, again, I don't know how many electrons there are, but I'm just going to put 3 in there for argument's sake. This is what we call the ground state, and there's energy on that axis there. These electrons in the lower part of this partially filled 3D subshell can be promoted to the upper part, and so it's promotion of an electron from lower level to the higher level. But the key thing you understand is that light is absorbed for that process to take place. So light, visible light, absorbed, and that results in promotion of electron to higher energy level. So one of them drops over there. We've got an excited state now. Now, then some of you talked about an emission of light as it drops back down again. That is not how transition metal colours come about. That's how flame test colours come about, and flame emission spectroscopy, all that's how that works. For transition metal colours, you've got to talk about simply that it's the complementary colour that's seen. So you assume you shine white light at it, one colour is absorbed, and the resultant, the remaining colours are seen. So all you've got to say is that the complementary colour to that absorbed is seen. I've made a little video on walking people through that, so if that's not very helpful, a slightly longer video that I can share with you, just ask please if you want me to. And now this one I just need to look at. Right, so ask you to refer to this question, ask you to refer to sections 5 and 15. So section 5 shows you that there's the sort of colour part of the electromagnetic spectrum, and the violet end is the shortest wavelength with the highest energy, and it's asking which is the one with the highest energy. So it's the one where violet is absorbed, and we look at then the colour wheel, and opposite the colour wheel is yellow, and so of the compounds on the previous page, the one that's yellow is the top one. CO with 6 ammonias is the complex, is 3 fluoride ions as well. So I was expecting you to give either that or the mark scheme says that as the answer, because that's the one that's yellow. It opposes, is the opposite on the colour. Remember, the colours is the complementary colour that's observed. State and explain in which the complex ions that transition to responsible for highest energy. So what does it say in the mark scheme? You get a mark for saying that, and you said because this absorbs as it absorbs the shortest wavelength. Blue, purple wavelength. It even says 424 on there. As long as you say shortest wavelength, highest energy, shortest wavelength, or highest energy, something like that. Okay. Question 5. Heptadecane. Balanced equation was not a problem for most people. It's complete combustion, so you should know that the two products are going to be carbon dioxide and water. We need oxygen for that, just get to working out how many. But we're going to get 17 carbon dioxides because there's 17 carbons there. We're going to get 18 waters because there's 36 hydrogens over there. All you've got to do is tot up the oxygens, 34, add 18, 52, divided by 2 is 26. Divided by 2 because 2. The enthalpy of combustion is that. Calculate the maximum energy produced when we've got 2 grams of that combusted. So the first thing to do is to work out how many moles that is. The number of moles of C17H36 is 2 divided by the formula mass of that thing, which is 240.53, and that comes to, you get a mark for this, so 0.00831 moles, and that's the amount of energy released when you burn 1 mole. All you do is multiply those two numbers together, and you end up with 94.4 kilojoules. What's the maximum temperature change? When, just say that loads of people put minus here. It just says the maximum energy produced. So you just need a number here. You don't need a sign. This is essentially Q, isn't it? Right. Determine the maximum temperature change when 500 centimeters cubed of water is heated by 2 grams. Right. Just going back to the energetics topic, year 12 stuff. So Q, which we've just worked out, is equal to M times C times delta T. And 3 cheers to the person who used the value of speed of light for C. But C is specific heat capacity of water, which is 4.18. We're told we've got 500 centimeters cubed, which by the way is equal to 500 grams of water. It's the water that's heated, not the 2 gram sample. That's what's being burned. So we've got to remember we use Q. Physics students have approached this slightly differently, but in chemistry we've always used Q in joules. So 94,400 joules. The mass is 500 grams, 4.18 for the specific heat capacity, and that would be delta T like that. Rearrange that. Delta T is equal to 94,400 divided by 500 times 4.18, and that comes to roughly 45 Kelvin, 45 degrees C. Okay. Somebody converted 45 degrees C and then added 273 to it. That value, the value for change in temperature is the same whether it's degrees C or Kelvin. There's lots of assumptions you've made there, and many of you got lots of these. So I'm just going to read these out. So water does not evaporate. So if you're doing a sort of calorimetry experiment, some of the water you're heating up might evaporate. Big one, the main one probably is we assume that heat is not lost to surroundings. We assume that all of the heat is transferred to the water, which is the same as saying there's no heat lost to surroundings. We assume the density of water is 1 gram per centimetre cube. We've converted this to 500 grams. We assume the water is pure and therefore would have the right specific heat capacity. And we assume that complete combustion is taking place. Most of you got at least one of those or 2 of those. Biofuels, though, were a bit of a disaster for you. The vast majority of you thought that biofuels don't release carbon dioxide. That's just not true. So biofuels are things like wood, they're oil made from plants, and when you burn wood and you burn fuel from oil from plants, they contain carbons, they contain hydrocarbons, and when you burn them, they release carbon dioxide. So it cannot be right that they don't release carbon dioxide. The key thing, though, is biofuels, when they're being made, are taking in carbon dioxide through a process that I think you've probably heard of called photosynthesis. So I'm not going to write it all out, but some talk about photosynthesis going on when the plant is growing and will take in carbon dioxide from the atmosphere. And it's carbon neutral. They're carbon neutral because the same amount of carbon dioxide is being removed from the climate when the plant is growing as is released approximately when they're being burnt. Enough of that. Determine the standard enthalpy change for the reaction stated. So most of you for this question did what I would have done, which is to set it out as I've taught you, work out the total number of carbon-carbon, carbon-hydrogen, single, double bonds, whatever, and totted it out properly. If you're not sure how to do bond energy calculations though, and you get this question wrong, you need to review that skill. The way it's done in the mark scheme is it's just recognising that the products have got almost the same things as the reactant. So there are still, in the products, 36 CH bonds. So it just cancels them out. 36 CH bonds in the product and the reactant. So it doesn't bother working those out. And so the values I've got both versions actually here. So the values in the values in the mark scheme are simply the energy of the bonds broken. It just accounts the 4 carbon-carbon single bonds that are broken, which comes to 4 lots of 436. You top that up and it comes to, I don't have a number for that. And then the bonds that are being formed are 2 lots of carbon-carbon double bonds in the products. Usually the reactants take away products, you get the right answer. Most of you, though, worked out all of the bonds in the reactants, all of the bonds in the products, and those 2 numbers are 20,000, I think it's 20,440, which I gave a mark for if you got it. The bonds in the products, 20,284, and it's because bond forming is bond breaking is endothermic and bond forming is exothermic. That side, take away that side, and you end up with 156 kilojoules per mole. But please, this comes up. This question comes up so much, and I've sort of rushed through that question a little bit. I'm going to spend ages totting up all of that in this question. But you've got to be really confident doing bond energy calculations. You are able to do them, all of you, every single one of you. You must go into the exam knowing how to do them. Part II. Determine the enthalpy change for the reaction using the data in section 13. Let's look at section 13. So the equation in here is delta H for a reaction equal to the sum of the enthalpy changes of formation of the products. Take away the sum of the enthalpy change of formation for the reactants. The products are one lot of that stuff, which is this number here, and two lots of ethene, which we have to get from the data book, which is plus 52. But there are two of them. And then we take away the enthalpy change of formation of the reactants, which is and that, if I've done it right, comes to 186 or thereabouts. Just going to check the answer. 186.4 kilojoules per mole. Comment on the difference between the two values. This is getting the difference, getting the idea that bond energies are average values. Most of you got that actually, so well done. Again, the next question, predict the entropy sign of the reaction. If we look at the reaction, we've got one molecule of gas on the left hand side and three molecules of gas on the right hand side. If we say that, so 1 to 3 moles or molecules of gas, and so you get an increased entropy to positive delta S. Okay. Discuss how temperature affects spontaneity. So this is quite a difficult question to get the marks. So the first point I'll make is that DII, it tells you to refer to DII and DIV. So for heaven's sake, please comment on those. So delta H is positive and delta S is positive. So make sure you make that really clear in your answer here. And this is therefore a question about delta G is related to delta H minus T delta S. And you have to show an understanding that the reaction becomes spontaneous or more spontaneous if delta G is less than 0 or negative, right? So equals spontaneous. Right, so let's think about this. So delta H is a positive value there, and so in order for delta G to be negative, this term here, this T delta S, must be a bigger value than delta H. Now delta S is a positive number, so take away a positive number, that's all fine, but the bigger T gets, the more likely it is that delta G is going to be a negative number. In other words, the bigger T gets, you multiply it by S, eventually that becomes a bigger number, and this one, that, take away that, becomes a negative number, right? So all you have to say here is that at higher temperatures, or as temperature increases, the spontaneity increases, or more likely to be, delta G is more likely to be negative, and that increases the chance of being spontaneous. This question was done well, so ethene C2H4. I know I said there's not any organic, a little tiny bit didn't hurt you. Ideally you would be writing steam there. You might have even written the fact that there's an acid catalyst over the top. You were just asked to write the equation there, C2H5O8. Some of you wrote C2H6O, which I didn't mind, but I quite like it being written out like that so you can see that it's ethanol. You know what ethanol is. Ethanol will react to form an ester with a carboxylic acid, GCSE chemistry this, and we've not done much of this lately yet. We're going to do a bit more practice of organic chemistry certainly, but this is a condensation reaction. This was really a problem for people. People really struggled with this question. No, there'd be no organic, but condensation reaction. And X, if you just worked it out, you just totted it all up, you realise it had to be water. The atom economy was a calculation. So for the atom economy, you add together the formula mass, well, you work out the formula mass of the product you want, which is, if I can find it, 310.58. Again, encourage you to use 2dp. divided by the total formula mass of either all of the products or all of the reactants. It doesn't matter, it's the same thing, but that comes to 310 add 18.02, whatever that is. So 310.58 plus 18.02. You times that all by 100 because it's a percentage calculation, and that comes to 94.5%. Pretty highly atom economic reaction. The only waste product is water. Why is atom economy important? It's all a measure of how much waste there is. So lots of possible answers here. So sustainable development, more economical, more efficient, reduces waste, better use of natural resources, any of those sorts of things will do. And case C for this reaction is the concentration of the products, which is C17H33COO CH2 CH3, I think, times by the concentration of water. Many people missed out the concentration of water, which you do for things like Ka, because water's the solvent. Water's not the solvent here. This is done in a direct reaction, so we need to include the concentration of water here. I can understand why people didn't from what they've seen before, but that only applies when water's the solvent. There is no solvent for this reaction that's been mentioned anywhere. And the clue is you're told it's liquids. And CH3CH2OH, that's that one. Also, you got that right. The only people got it wrong just missed out the water. Hopefully you fix that now. And you're told the Kc is that value there. Determine the amount of the ester present when you've got that much oleic acid and that concentration of ethanol. So the calculation there was pretty straightforward. You simply have to plug the numbers into what you just did. So I've filled the numbers in to save a little bit of time. So they're the numbers. So that's Kc as given. This is what we've got to work out. We're not told this. We are told the concentration of oleic acid and ethanol at the start of the reaction at least, and this is important in a second. If you work that through, you end up with the concentration of those two things being equal to 9.3 times 10 to the minus 7. So just popping those numbers up there, so timesing by minus 0.01 in total. But the concentration of this and this are the same as each other. That's not an assumption, that's a fact. Okay, so the concentration of those are the same. So we can say the concentration of C17H33 COOC2H5, just shorten it a little bit, squared is equal to that number I've just said, or we can just make it the square root of the number that I just said, so 9.3 times 10 to the minus 7. And if you do that, you end up with the right answer, which is, oops, the button there, so 9.64 times 10 to the minus 4 moles per decimeter cubed. So it's not an assumption that water and ester are the same concentration, because they are. Okay, water's not a solvent here. What we've assumed, quite reasonably, because this value is tiny, that this equilibrium lies very, very much to the left, and therefore these numbers, 0.1 and 0.1, which were the initial concentrations of oleic acid and ethanol, are the same as the concentrations at equilibrium. Remember this Kc here, these should all be the equilibrium concentrations, and we're using in the calculation the initial concentrations. So because the concentration has not gone down very much, it's perfectly reasonable to say put the values of the initial concentrations in there. Alright, one method of increasing the yield, that's just Le Chatelier. If you look at the reaction to increase the yield, well, you could either remove the water from the reaction, and that will pull the equilibrium to the right, increasing the yield of this stuff, or you can increase the concentration of this stuff or this stuff. So the answer is increase the concentration of either reactant or remove water. That'll do. That's the end. 1 hour.